That's how much I can say in Estonian, but I'm very glad that I'm here and that I have the opportunity to talk about our work, which was done very much in collaboration with Guillaume, which just comes on. And what I will talking about is how we can trace the mass distribution in the nearby universe using galaxy clusters actually that are observed in X-rays. To illustrate you, and I will talk about several things. I will start to talk about the monopole of the density distribution, then go to the quadrupole, which we will see is a sort of extended local supercluster. And then we will look how we can characterize superstructures, superclusters in the nearby universe out to a redshift of 0.03, something that was pioneered by Young here in the audience. And we are looking at just with a different eye at the later epoch. And to illustrate that galaxy clusters trace the large-scale structures very well, I use the Millennium simulations, computer simulations, and body simulations that have been done quite a while ago. And you see here density maps of the large-scale structures. These are slices through the simulation cube of the Millennium simulations. The red filaments are the densest regions that we see over here in the picture. And then you see these black spots, and these are galaxy clusters with a mass roughly above 10 to the 14 solar masses. And you can see that the galaxy clusters really sit in the densest spots in the large-scale structure. We can quantify that a little bit more. We take the simulation, we cut out boxes. On the left-hand side, the box has a side length of about 90 megaparsecs. On the right side, the box has a side length of about 180 megaparsecs. We plot the overdensity of the dark matter on the x-axis, and we plot the overdensity in the number counts of galaxy clusters on the y-axis, and we can see that there is a nice correlation. If we take the smaller boxes, we have Poisson noise because we don't have too many galaxy clusters. If the boxes become larger, the scatter becomes less, and the scatter is approximately quite well characterizable by a Poisson noise. So we are very well set to trace large-scale structure, and we have an idea about the uncertainty with which we can do it. And now we need, of course, a survey that gives us galaxy clusters in a complete way and with a very clear selection function. And we get that from the ROSAT All-Sky survey. We have followed up the X-ray sources. In total, there are about 150,000 X-ray sources in the ROSAT survey. We have identified, going from the highest flux, X-ray flux down, we have identified about 2,000 galaxy clusters in the survey by verifying optically that they are really galaxy concentrations in 3D, and we also measure the redshift in the optical, and then with several tests show that we are most probably much more complete than 90% as a flux limited survey. Flux limit means that in high luminosity clusters we see out to a large distance. Low luminosity clusters we only see nearby. But we have a good feel for how we are selecting them. And that is now sort of a 3D representation of the galaxy clusters, and I can animate that a little bit. And the distribution of the galaxy clusters is surely not a Poissonian distribution. With your eye, see that there's a lot of clumping, there's a lot of large-scale structure in the distribution of galaxy clusters. And this we can now use in a similar way as we have looked in the simulations in the large-scale structure. We can use this cluster to trace the large-scale structure in the nearby universe. Just stop it. Okay, this gives you an idea about the selection function. So for a flux limit, we are highly complete to this flux limit. with the numbers given for experts. And we ask for, at this flux limit, we ask for at least 20 X-ray photons. We have a very clean sky. There is the density of photons in the sky is relatively low. So with 20 counts, we have a good feeling that it's with a high significance of a source, we can get a relatively good flux and luminosity, at least to about 20%. And we can, for a large fraction of the sources, we see that the source is not a point source, but it's extended. But we cannot say that for all the sources, and this is why we really need large work to identify the galaxy clusters also in the optical. And so this gives us a selection function, and you see here the fraction of the sky covered out down to a certain flux limit. We cut here, we throw the clusters with low fluxes away when we are not complete in following them up. And for little part of the sky, we don't reach the flux limit, but that is well quantified, and we can put that in the selection function, and we can account for that.
It's just for a small question. The track the photons, how long is the exposure?
The exposure.
Yeah.
The exposure is mean exposure is between 400 and 500 seconds. But in some areas, I think this especially comes from the fact that the satellite is a low orbit, and it sometimes goes through the radiation belt. They shut off the instruments because they don't want to have them damaged from the particle flux in the radiation belts. And that is geographically in certain regions of the sky. And that is why you have these deficits in the exposure time. And just as a test that we get a relatively clean sample with including the corrections for these partly missing galaxy clusters. We plot here the galaxy cluster density of the function of the interstellar column density. That means here on the right-hand side, high column densities are the ones where you get close to the galactic plane. Everything is off plus minus 20 degrees from the galactic plane. Where we are doing really quantitative work. We have partly also filled these regions, and part of our plots will show results where we have 2/3 of the white region has been filled with clusters, which are a cluster survey, which is about 70% complete, but then it just gets too difficult. And we qualitatively also fold these results in, but we also always check quantitatively, do our conclusions hold with the well-defined part of our survey. And if we, for that survey, plot the cluster density as a function of NH, we see that there's not much of a deficit. Of course, there the sky regions are small and the noise get larger, but we don't see a deficit. If you do the same for A-belt clusters, for example, and plot them as a function of galactic latitude also, you see that the number density would go down. So this is a big motivation to use our survey and to look at structures again that have already been found before, for example, by Young and his group and by ROSAT. But we try to quantify them now through galaxy clusters. So I have shown this yesterday already. One of the statistics that comes out of the survey is a galaxy cluster X-ray luminosity function, and it's just how many galaxy clusters we find as a function of X-ray luminosity. It's a differential function, so we find a large density of less luminous clusters, and the function dives down very rapidly if we go to the most massive and most luminous galaxy clusters. And the line that is going through it is a fit from a cosmological model with the parameters given above. So things look, we can sort of explain the number of galaxy clusters of a certain X-ray luminosity, which is tightly correlated to the mass of a galaxy clusters. We can predict this number very well just going to a popular cosmology model and retrieve it. So we have a good feeling that we are on a good track. The next curve is now starting to explore the nearby universe, and what we plot here in this curve is just the density of galaxy clusters, as a function of redshift. The first thing we realized, it's relatively homogeneous. Again, it's a good quality test of our survey that we find a homogeneous universe on large scale. But especially nearby, where we should actually be best to trace a structure, we have a deficit. And the green point and the blue point here, it's, of course, sometimes you see it on the large error bars. We have not a very high number density of galaxy clusters in these small volumina hereby, volumes hereby. And this is taking the Virgo cluster out or leaving it in. Virgo cluster actually as 3 entities, we take Virgo cluster and N49 as 2 different units. And so we see this deficit over here, and that is a deficit in the number counts of galaxy clusters, in the number density of galaxy clusters. So galaxy clusters follow the large-scale structure proportionally what is a bias. And you can calculate this bias theoretically. So roughly, there is a bias between 1.6 and 2. It's about 1.6 and 2, that the galaxy cluster fluctuation amplitude is about a factor of 1.6 to 2 larger than the amplitude of the underlying density variations. And we can also fold that in, and then we get this deficit for galaxy clusters, which is orange, with the statistical error bars. It's basically Poissonian errors. And then the green curve is what we expect for the underlying dark matter, which is where the amplitude is smaller for the density fluctuations, but still we get a deficit of up to 30% over here. And now I want to go a little bit more in the method that we have been applying to reproduce this curve for a flux-limited survey. Here we again have the luminosity function of the galaxy clusters, and we only take galaxy clusters above 2 times 10 to the roughly 2 times 10 to the 44 ergs per second above this dotted line. But the more we go out, the more we are missing the less luminous objects. So in effect, if we go out to larger redshift, we are volume limit. We have all the galaxy clusters at this minimum luminosity only out to about 0.016, and then at the lower limit for the X-ray luminosity increases. So we want to correct for that, and we do that by using a weighting function. We normalize everything to the density of the galaxy clusters at the lower limit, but we look how far do we reach at a certain redshift in a certain sky location in sampling galaxy clusters of a certain luminosity. This is the minimum luminosity we get. We integrate over the luminosity function of what we can observe at a certain sky position and redshift, and then normalize it basically by the luminosity function integrated over the whole luminosity range up to the minimum luminosity. And from that we get a weighting factor, and every galaxy cluster that's too far away is outside the volume limited sample, it's in the flux limited sample, so gets a weight for what we are missing. And that is how we correct our flux limited sample to make it basically that we can assign a density, cluster density that is not dependent on the redshift. And that is what we get to check that everything is well behaved without going into too much details. We can go to higher flux limit where we have a volume limit of our sample, where we have all the clusters at this luminosity limit in our sample out to a certain redshift. We only plot the points which are volume limited, and if we go to very high flux limit, we can trace it very well outside. So we reproduce this deficit for different X-ray luminosity limited subsamples of our survey. So we are sort of really stable in recovering this deficit. Please ask if something goes too fast. And now we can look how this is behaving in north and south. And I always knew, even if one looks in the Abel catalog, there is quite a north-south asymmetry of how many nearby Abel clusters you find in the north. There are much more than you find in the south. And that is now reflected in this deficit of the nearby matter density in the universe. If we look in the north, we have a deficit that is relatively small, and roughly this is at about 80 megaparsecs. We recover almost mean density, and that means if you look into the structure of the universe, this is a underdensity that goes out roughly to the Great Wall and the Coma cluster, Coma supercluster. In the region from us to there, you have a deficit, but once you reach the superclusters and integrate it into your mean density, you recover roughly mean density. In the south, you have a larger void, because there you have to go out to the distance of the Shapley supercluster, and in other parts of the sky, also similar distance in the Shapley supercluster, we find two other relatively large superstructures. So here you go out, you have an large void, and there you have to go out to about 140 megaparsec, and then you actually hit an over. This is cumulative, but if I would have it differentially, there you hit an overdensity from these superclusters, and they make up for the deficit that we have nearby. So this is, you have to go at least out this far in the south 140 megaparsecs, in the north 180 megaparsecs to reach mean density of the universe. If you stay inside, density is too low. That has been found by other people, but they have looked in the galaxy distribution, and one of the big problems of the galaxy distributions is you really have to have a very homogeneous calibration of your magnitudes and of your selection function. And that's not so easy, especially across the whole sky, because you usually have only a hemisphere that's a little bit more than a hemisphere that is accessible to one telescope. So we don't have this monopole, the density, matter density traced for the monopole for galaxies so easily, but one of the best things that have been published is by Whitburn and Shanks, using three different regions, the South Galactic Pole region, the North Galactic Pole region, which is over here, and that is the North Galactic Pole region in the northern sky. We will compare mostly to these two things here. And if you look at the South Galactic Pole, you actually see a relatively large void in the galaxy density distribution. Yes.
Is that where the local point is located inside?
Probably, maybe you can answer it better.
There are both northern local void and southern local void. And when you go to south, there are also the Seridanus void and other big voids.
So so you see this deficit not in all direction, and you see it very pronounced in the South Galactic Pole. And that's the galaxy density distribution. If we use our galaxy clusters and plot it on top of the galaxies are plotted here, the blue points are ours. If we just cut out this region and plot our density structure over, it looks very similar. And it's very encouraging, but of course, the smaller the region is, the smaller the number of galaxy clusters get. And we are running out of significance to trace things on relatively small scales, but it's surprisingly similar. And again, if you go to the North Galactic region, this red region over here, from the 6-degree field galaxy redshift survey, galaxy people see not much variations, and we don't see much variations. So things seem to be coming up in other surveys too. Then the next thing you can look at is people have tried to reconstruct the large-scale structure in the universe. This is the Bayesian reconstruction by Jens Jasche and Labour, for example. It's based on the two-mass galaxy redshift survey, and they get this density as a function of radius function, the monopole over here, and this is the region in which we get an underdensity. They see, apart from this peak, which may be the Great Wall, they also see more underdensity than overdensity. Not as strong as our, but we have large error bars on our underdensity. So it's, and this is also sort of recovered here. So other people are finding similar things. And now the question is, what is the significance for any cosmology measurement that if we are sitting in an underdensity? And I think the most interesting point is the measurement of the Hubble constant. And if you measure a Hubble constant and you are measuring the Hubble constant within a volume that is underdense, the expansion of this underdensity is faster than the expansion of the whole universe. This idea, I mean, this thing came up as soon as people discovered the accelerating universe, with here the data set of Perlmutter, or the other group with Brian Smith. They see a sort of a curved structure that gives you a universe with lambda. You can also try to fit another curve through the data, which would be consistent with an Einstein de Sitter universe, so with a lambda of 0, and that would be, if we fit it over here in the nearby universe, it would be a little bit lower than the data points. So if you want to, I mean, this is old discussion, but if you want to discuss the whole lambda business away, you need a void, a local void, which a radius of about 300 megaparsec and underdensity of a factor of 2. This is much too extreme compared to what we find. So we can actually rule that very securely out as an explanation. But still, it's interesting to see what a local underdensity means in terms of the Hubble constant, because we have the Hubble constant controversy. People who measure it with Cepheids in the local universe, they get a value of 73, 72 or something, while a very accurate number comes from the Planck survey, and they get a number of 67. And the error bars they give, which often are underestimated, but what they give gives you, I think was at least a 5 sigma tension. And the question is that real or is it systematic? And one of the things is, of course, if we have an underdensity in the universe, we would be on this side, which gives you a higher Hubble constant. This is much more exaggerated. What we get, what is implied by the underdensity we have would be not so easy visible on the plot. But this is the effect we get from an underdense universe. So we are very interested if that has to be folded into the Hubble constant. But this is just reminding you of the controversy that these are all the nearby numbers, and then we have these are all the numbers from nearby surveys, and this is a number that we get from the Planck survey, and that hasn't changed in newer publications. And just to update things, there is a new review article from this year by Wendy Friedman and Barry Mador, and they now show the different type of Hubble constant from different nearby surveys compared to the Planck value. This includes now also observations by JWST, where they are already correcting a little bit HST measurements, but basically they are still at a similar redshift. For example, the group around Adam Rees still gets a Hubble constant of 73, and this is another measurement, but I think this is still in its infancy that comes from gravitational waves of neutron stars. But what we find, this local underdensity of the universe cannot explain the Hubble this Hubble constant discrepancy, because the small overdensity we find would only account for 30–40% of the discrepancy. So it's a small effect, but should be folded in at a certain point. But we had correspondence, both Tom Shanks and I had correspondence with Adam Rees. He doesn't like another density in the local universe because, if I go back, because in their data, they don't see anything, when they should see a little kink where this answer density starts, and he claims that he doesn't see it. But I mean, if you look at this data, but this is Cepheids and this is tip of the red giant branch data, you have some room for a higher Hubble constant here. And for example, Tully, which is also working on large-scale structure, when he's modeling the nearby universe, he's modeling it with a Hubble constant of 75. So we are very curious if better measurements of supernova finally find a sort of kink in the nearby universe, but that is still to come. So the next question is, how likely is such an underdensity? And you can just do standard structure formation theory, and you can calculate the variance of the dark matter as a function of the scale, and you can calculate from this variance how probably is it to see an underdensity of about 15–20% that we see. This may be a little bit on the exaggerated side, but anyway, if you do that, it's you get that this is a 1.322 sigma effect, so it's a little bit rare to find such an underdensity, but it's absolutely probable. It's not improbable to find it. Okay, and this is just another calculation where people have quite identified. What I just showed was then our analytical calculation. You can go into n-body simulations, and you can see that to have a Hubble constant that is off by about 2%. But 2% within a radius of 125 megaparsec is as much of as we have it. The variance is about 2%. Anyway, so it's a little bit improbable. So it's not standard that you would find this underdensity, but it's still not improbable. Now it's interesting to look now at the monopole, and one of the striking things is to look in papers, for example, from Ellen Courtois, who works with Tully. This what is striking, and maybe we can talk about it, Jan, later on. It's very striking that if you look into the very nearby universe at just 6 megaparsec, you find all the galaxy groups ordered in one plane. And that is then embedded in the local supercluster, which has first been described by Couleur. And then you find that there is also some structure which is much larger, and you could call the extended supercluster. That is something we discussed in the last 2 days with Jan and Marit. They early found such a structure also very early in a similar way. But this is appears in one of the cosmic flow papers. This is an old publication from Tully finding something like that. And this is work by Peter Shaver and Marc Pierre. And they look at radio galaxies, bright radio galaxies from the Molonglo radio catalog, and they see that there is a strong segregation of radio galaxies towards the supergalactic plane. Tully claims that this is a really very large structure with a diameter of 360 megaparsecs, almost. We were very curious what we see if we trace it with our galaxy clusters. And that is shown here in a way that we plot our galaxy clusters onto the sky in various redshift slices. And the galaxy clusters that we find are the round dots. If they are, the filled ones are in the supergalactic equator, plus minus 20 degrees. The open ones are outside. And the colored areas are colored by the density of the galaxy clusters. And these lines, the black lines, give you this the region of plus minus 20 degrees around the supergalactic equator, which the equator itself is shown by this blue dashed line. So if we look at very nearby, out to redshift of 0.02, we see that the overdense regions are all lying in the supergalactic plane. If we go a little bit further out, which is shown here, we have the Great Wall. This is Centaurus and Perseus, actually. We have the Great Wall entering, still filling something into the supergalactic plane. But if we go beyond 0.025, we actually have more underdense regions in this ring than outside. And that is roughly a distance of about 100 megaparsec. But we can quantify it in different ways. This is again showing the cluster distribution as a function of galactic latitude. I showed it similar way as a function of interstellar medium column density. If we go into the area which is not well sampled, we are losing objects, but these are more distant clusters and we have a deficit of them. But if we look in just at the nearby clusters out to a redshift of 0.07, we are not so incomplete at the nearby universe, and we can include them at least in some of our pictures that we show. This is now the cluster density as a function of supergalactic latitude, and you see it's very strongly segregated towards the supergalactic plane. And then we look how far does it go, and we have a slice now, so, which is plus minus 20 megaparsec around the supergalactic plane, and we look at the galaxy cluster density in the supergalactic plane, and that's shown in red. And then the cluster density outside the supergalactic plane is shown in blue. And we can see, of course, both are diving down nearby, but that is just our underdensity traced again. But if you look out to about 100 megaparsec, the cluster density inside the supergalactic plane is definitely higher than outside. But at around 100 megaparsec, so the next points, it's reversed. There is more, the cluster density outside is more. So I think this shows for us quite well that this sheet, which starts at 6 megaparsec, goes on, ends somewhere around 100 megaparsec. And sorry, yeah, okay. And this, now we are looking into the plane, and we are looking what is the structure inside the plane, and you can see these are just all the galaxy clusters inside this sheet or in the supergalactic plane, plus minus 25 megaparsec. And we have the coma cluster is this green stuff. The open simples are the clusters outside the supergalactic plane. Centaurus is completely embedded in the supergalactic plane, and Perseus-Pisces, that sits over here, is also very well embedded. So actually, these two structures, Centaurus and Perseus-Pisces, make up most of the matter in the supergalactic plane. So this pancake is actually a structure in itself, and in form of these two superstructures that are embedded in the pancake. And I think I skipped that. This is just Laniakea, and it shows basically Perseus-Pisces and Centaurus here as the two things in the supergalactic plane. And then the next, which is partly contributing to the supergalactic plane, is this object over here. We are looking at the Perseus-Pisces cluster. here, and it's a long structure. It's something that Jan has discovered or published 1978, and it's the largest of the structure nearby. We will see more about it. This is sometimes called the Southern Great Wall, but here called the Abel 400 supercluster. And one of the things, just teasing your appetite, because it is something we didn't follow up, but I think Jan looked at this very early, he told me yesterday, is if you look at the Perseus supercluster and plot it in terms of the galaxy distribution, and then if you have a label of the galaxy, what galaxy types they are, and this comes from an epoch where it's not done by colors or not done by computer, but people typed it by eye. Early type galaxies trace this backbone of the structure very sharply and very well. And the more you go to late types, the more it's diffused. So these superstructures they are not a collection of clusters, just a collection of clusters. They are special environments, and this really shows that the type of galaxy traces the whole special environment, the whole superstructure with all the connections, and not only the clusters itself and the highest density regions. And now we want to characterize the superstructures in the whole volume out to redshift 0.03. And we have to find a way how to do that. We have a flux limit. We don't have a volume limited sample, but a flux limited sample. So we have to take care that the cluster density gets more and more sparse when we go out in redshift. So we cannot just apply simply a friends of friends algorithm, the most popular algorithm to describe these large scale structures, but we have a weighted one. And so I told you before how we calculate a weighting factor, and this weighting factor is now used to scale the linking length. So the weighting factor tells us basically how much underdense the cluster distribution is, because we don't sample all the clusters. And this goes into the cube root, into the linking lengths of the galaxy clusters. And so we have a varying linking length, which basically gets larger and larger to go out in redshift. Redshift range is not so large, and so linking lengths over what we are talking about is changing by a factor of 3 or so. It's not so bad. And we normalize it to get superstructures. We normalize it at low redshift, where we have reached the minimum luminosity. In our sample, we normalize it to 19 megaparsec, but then it's increasing if you go out. And if you look to some mathematics, you find out this should roughly correspond to an overdensity of the galaxy clusters of about at least a factor of 2 or more. And so it's a relatively low overdensity. It tells you, when we both your group and our group looked into when does a structure collapse, and the structure would collapse if you have an overdensity in the matter of more than 7. So these are relatively underdense structure, and they are transient structures, but still they are interesting structures. If you do that, you get about and we ask that these units have more than at least more than 5 members to call it a supercluster. We get 8 structures sticking out to this redshift over here, and they have masses of that, lengths of that, and the most prominent ones are Perseus-Pisces, one of the first ones that have been known, Centaurus, Great Wall or Coma supercluster, and Hercules. And then we have smaller things. The Virgo cluster, actually, if I'm very strict with my criteria, it shouldn't actually appear. We were a little bit generous to get the Virgo cluster in, the local supercluster, and the Southern Great Wall over here, and 2 new structures, Sagittarius and Lacerta. One of them is very much in the zone of avoidance and has not been seen before. They are new, but they are smaller. And the largest of all is still the Perseus Perseus-Pisces supercluster, which we see over here. And the other very large structure is Hercules, but I think what we see over here is Hercules is blue over here, and it has lots of members which are at higher redshift and are actually outside our search volume. We know it continues to higher redshift and becomes also a very large structure. This is a same thing. Oh, sorry, I'm going backwards. This is the same thing in galactic coordinates. I don't want to say too much, but again, we have the Perseus-Pisces supercluster here. And depending on how we are tuning things, I come to that later, this structure is sometimes included, and we get an upturn of this large-scale filament, upturn that it returns back to the zone of avoidance here. And that we can see actually in a galaxy survey that has been done by René Grant-Korteweg, who is very much interested in getting galaxies in the zone of avoidance. They find actually a structure. There's this cluster over here that is outside our linking lengths, and they find this upturn over here. But this is where we also find another group that could be linked, but it's not linked in our prime method. But so this is, among all the superclusters that we find, this is the most filamentary one. Okay, this is a 3D view. Again, Perseus-Pisces over here, Centaurus. So that's a local sheet. Hercules is very much up, but still you see that a lot of things are concentrated in the middle, in the supergalactic plane. And this is a comparison, but one of the things I did is if I take one of the early reports by Ord from '83, and I think that includes a lot of results from Jan and his group about the structures. They find the local superclusters, Perseus-Pisces, Coma supercluster, Hydra Centaurus. But they connect Hydra to what we call the Centaurus supercluster and Hercules, and they find this sort of lengths, for example, and we get sometimes a little bit more clusters connected or sometimes a little bit less clusters connected. But I think what has been found in the early days is actually very stable and is very nice characterized, and we just do it in another way, and with a little bit more quantitative, we find very similar things. Here you have the masses, and maybe I don't go too much into the detail. I did one more exercise, and that is how stable are, how much do these structures rely that I have a certain linking length or a certain minimum X-ray luminosity. For example, if I throw out more of the low luminosity objects, of course, then the density distribution gets more sparse. I have to take a larger linking length to get the same overdensity of structures. And we varied that by a factor of 10. We went from the lowest X-ray luminosity, like 10 to the 42, to 10 to the 44, in 43 in 7 steps. And we looked how much of the structure is retained, but I'll just talk about the end of the whole thing. So this is Perseus-Pisces, and if we actually increase the luminosity, we lose these guys, but then we get a few more things linked to the structure, and we get actually this upturn. This is for Hydra Centaurus. We lose some objects here, but then it becomes a larger structure. It connects to the Virgo cluster, will be connected into the Centaurus cluster. And this is the Hydra cluster will be connected in this complex. So but the complex is somehow stable. It just develops slightly different lengths. And this is the same with the Great Wall or Coma supercluster. So for the big superstructures, they are actually very stable in how you characterize them by friends-to-friends method. And if you take only the most luminous clusters, or you go down to less luminous objects. And I think I'll skip that and just go to the conclusions. So I think, I hope I convinced you that galaxy clusters provide a powerful tool to study the large-scale structure. And it seems to indicate that we live in an underdense universe, which goes out to about 100 megaparsec. This underdensity is very much segregated towards the supergalactic plane. And the most massive structure that we find in the volume we have studied is the Perseus-Pisces superstructure, which lies actually mostly in this region, and the other large structure in this nearby region, in this pancake, is Centaurus. And yeah, and I showed you the 8 superstructures in total that we find in the nearby universe out to a redshift of 0.03. And with that, I'd like to end my talk and thank you for your attention.
Thank you. And now questions, comments? People online can just speak up or write their questions to the chat.
Did you check if the properties of clusters within superclusters and that are outside the superclusters, they have any difference in their properties?
This is something that unfortunately Guillaume is not here, but she has studied that in detail. We find a small difference. So I think that the red dash curve is the cumulative X-ray luminosity function. You can directly convert it to a mass function with our X-ray luminosity mass relation. And you see there are a little bit more massive superclusters in clusters in the supercluster, but it's not really very significant. But Guillaume did work on the whole reflex survey, which is our whole southern survey to larger redshifts. She looked at higher overdensities, not overdensities of a factor of 2, but more overdensities of a factor of 7. And he finds a big difference. So this is the cumulative fraction of clusters above a certain X-ray luminosity. And clusters in superclusters are more top-heavy than the field. And she looked at the same properties in simulations, and she plots here. Here it's X-ray luminosity, here it's the mass that you know, and the mass in superclusters, the solid line, is more top-heavy than the mass in the field in between. So for this larger survey, higher overdensity, Guillaume finds a more significant result. This is, I think we would need a much larger volume and do more to make this result potentially significant. It's only a small glimpse.
So I have mistakes, but about the underdensity, the 1 megaparsec underdensity that you mentioned, and you asked how likely is that?
Yes.
Can you maybe please elaborate how would you model this likeliness?
Yeah. So since we use the galaxy clusters to talk about matter underdensity, I know the power spectrum of matter in the universe, and then I can say what is the density distribution if I cut out a certain sphere of the universe. It's a top hat, what's called a top hat window function in the literature. So I fold the power spectrum with the top hat window function and integrate, and then I get a variance as a function of the size of this top hat. So, and if I take a top hat of about 100 megaparsec, 120 megaparsec, I find that only in that I have to go out to 1.3 to 2 sigma out of the normal to get an underdensity in the way we see it. I have a little bit of feeling we are a little bit on the extreme side, and other things are not as extreme. And then you, I think it would fit better. But it's still, you would rather see, that's what the work of Wojtek, the simulation show. He asked a different question here. He doesn't answer what is a general probability if you are in the universe to find such an underdensity over density. He asked a question, what is the chance if I start from a local group? If I start already from a halo, then it's actually a little bit worse. So you would rather be a little bit overdense than underdense, but it's a small variation.
Yeah.
Maybe Moritz knows better than me. So I learned from your talk that the supergalactic plane is perpendicular to the galactic plane.
Exactly.
And the plane of galaxies is also perpendicular to the galactic, not really, but more or less at 0 order perpendicular to the galactic plane. So it's true that the plane of galaxies, it's not known if it's a transient structure also or not. But do you think there might be a connection? Like if we live in this super plane, we have accretion from this region and then. So has there been any work relating this plane of satellites with maybe?
For me, it's a coincidence. I mean,
It's just
I'm also surprised when I sort of reviewed the work. I was very surprised about, about this plot. I mean, this is just 6 megaparsec, and these are the local groups around our Milky Way. So this is a very small environment, and that's already in the same plane.
But it seems like the plane of satellites is at the same plane at the supergalactic plane, which for me, if I think of a continuous accretion, I would expect the majority of the matter to be accreted through the supergalactic plane. So it would make sense that satellites are aligned with the supergalactic plane, kind of.
I mean, it's a question. Why does everything have to be aligned in one plane on many scales?
Yeah, that's a question.
Yeah, and it could sort of break nearby. Well, I'm not sure. I mean, I'm already surprised that it's still aligned on 6 megaparsecs. So I wouldn't say it also has then to be aligned on 1 megaparsec scale. I'm not sure. But,
I had a question. Let's see. So is there like a center to this plane in 6 megaparsec, or like a center which is overdense compared to?
Again, this is another surprising thing. So why are we lying relatively close to the center of this structure? I mean, in the center of, in terms of the Z direction. In the center in X and Y, with this local thing, the nearby center is of course a Virgo cluster, first of all. But I mean, it's in a sense also, you could say it's a little bit surprising that we are roughly within the center in terms of the whole segregated structure. But
is there like galaxy clusters are so there are more galaxy clusters at the center compared to?
Yeah, if we use these coordinates, that this plane is supergalactic X and Y, and then Z is in this direction. So most of the matter is in this middle plane, and we are also in this middle plane.
And the plane of satellites is in that plane.
This I don't know the satellites of the Milky Way, but these are nearby groups of galaxies like M81, for example, and Andromeda is there in the same. And of all these groups, you see only 3 are outside the plane. But I'm surprised. I haven't seen much. I mean, I haven't looked up if this is discussed much more. Why is the coherence over so many scales there?
Within the XY plane, so my question is, within the XY plane, is it more dense at the center compared to the
I think the densest structures are per Perseus-Pisces and Centaurus, and they are away from us. So there's something on one side and there's something on this side. So there's not a, I mean, it's not going like the highest density peak is in the center of this structure. That's definitely not the case.
About the question, in the beginning, you said you calibrate your survey to get the weights, like the nearby region is more complete. And then, can you clarify, like you also say that in the center, the nearby region is underdense. So does it affect your weights? Like you calibrate using the region that's not atypical and then go further away?
I don't know exactly how to answer your question, but if I go back to this slide,
yeah,
one of the problems we have is we calibrate, of course, we know from interstellar current density that we get from 21 centimeters, for example, how much X-rays are absorbed. And we have the variation of the exposure of the X-ray survey. And that is, maybe one more back, this is modifying how far we can reach, or what is our flux limit. And over most of the sky, which is blue over here, we are reaching the flux limit, but we have some gaps over here. That is how we correct. And if everything would be well behaved with this correction, everything is clear. But to get this linking length weighting, we have one problem, and that is we have the luminosity function over here, and we use that to calculate the weight. Now, a problem is in the nearby universe, the low luminosity objects here come only from the nearby universe. So it's only defined by the region which is actually underdense. And if you look very closely, we dive a little bit below the best fit at the low density. And that may be already an indication that this luminosity function is too low over here. So if we use that to correct, we of course are moving in a circle by not correcting, by using the wrong function to correct, because it's underdense. And that is why we thought a lot about that, and I think it's not too bad what we are doing, but for exactly this reason, we use different volume limited samples, where the volume limit goes well beyond the redshift where we see the underdensity. For example, for this red things, this is a 10 times higher luminosity limit, and we recover that. So by doing that, we are making sure that we are not in a trap doing the wrong correction. And I'm not sure if that was what you asked, but
yeah, just to elaborate.
Yes.
On this question.
Yeah. So there is sort of an extra thinking and extra care one has to take there.
Also, maybe like we have this catalog of superclusters in Slow survey, and there is a rather large empty region in distance 200, 400. You see it's empty in the sense of lack of rich superclusters.
Yes.
And also know which clusters.
Yeah. Yeah, maybe it would be interesting to compare the properties of those. Of course, it's so far away, you cannot study it in such.
Yeah. I mean, that we would have to sit down and look at maps, or I mean, we are open to exchange things if you have questions or something which is sort of well described, we could look into our side.
Comments?
So, what is the size of this planar structure?
It's a radius of 100 megapascals, 100% of 70.
So is it possible, because this underdensity that you are measuring, it is spherically averaged. radius, like you're starting from around Milky Way and going away. So there is this planar overdensity, and when you are averaging in these radial shells, you are getting this underdensity because you are in a very specific region. And because the far away shells, you are taking the average of all these structures that is crossing voids, filaments, and everything. Suppose you go to some other place in the universe, say in a wall or a filament, and if you measure like the similar density plot from the center, you may again find these underdensities unless you are very specifically at the node. Is it possible?
Yes, I mean, you should in principle find both. You should find underdense regions and you should find overdense regions. I mean, what is happening here is that if we are nearby, the volume is very small and we are averaging over something small. The more we go out, the volume in the shell increases by the distance squared. So the volume rapidly becomes larger. And here we then are in a regime that the shell is large enough to average over everything. But we should see something similar if we start from another point in the universe. Except that this is a little bit, few of those cases should look like that. Other places should have smaller underdensity, other places, of course, should also have overdensity. But you should, if you are in a small volume, you should find large variations, which are then wiped out if you come to larger distances and shells with a large volume.